next talk is on spectrum and infrastructure sharing in multi-operator cellular networks, and will be given by ShanShan Wang, who is working at CNS in France.
Yes. Okay, my name is ShanShan Wang. I'm from the Laboratory of Signal and System. It is a joint laboratory which is supported by the University of Paris Saclay, CNIS, and Central Supelac, and the University of Paris Sud. So my topic today will be on spectral and infrastructure sharing in multi-operator cellular network. And this is a work supported by the 5G wireless ITN project, which is an European Commission. And you can find, if you are interested, you can find more details on the website, which is shown on my PPT. Okay, for the 5G wireless network, there are some critical requirements. The first is the data rate, which is the required bit rate for the application to function correctly, and the latency. Maximum tolerated time for a data package is generated at the source and to the time which it is received by the destination. And also the density, which means for the 5G wireless network, the high density is a critical requirement. And for the reliability, the maximum tolerant package loss rate at the application layer. Also, the positioning accuracy and the coverage is also some important problem. And today, my topic will be mainly focused on the data rate. Okay, this is an outline of this presentation. So first, I will give the description of the problem, and I will give a brief introduction to the stochastic geometry, which is the main tool that I use to solve the problem. Then I will present my system model. Then I will give you the results in the mathematical framework. Then I will give the more results to show that how my mathematical framework works and how it matches with the simulation results. Okay, here's the problem. Supposing that you have two operators in the network, and for the operator 1, it has many mobile terminals, and for the operator 2, there's much less mobile terminals. And it is clear that for operator 1, the base stations are overloaded, which means it already reaches saturation, and some of the mobile terminals cannot be served. And for operator 2, since the mobile terminals are much less, so it is not overloaded, and it has some unused resources, you can see. Some of the mobile terminals of operator 1 is not served, and for the operator 2, there are some unused resources. So the idea here is how to put this unserved mobile terminals and let them to use the resource of the operator 2. Okay, for the spectral and infrastructure sharing, we can have the unused mobile terminals in operator 1 to share the resources of operator 2. This sharing includes the infrastructure sharing, which you can see here. The mobile terminals can access to the operator 2, the infrastructure physically. And also, considering that they are sharing the spectrum, which means it can also, in some way, it can increase the data rate by increasing the bandwidth. But however, it will bring a problem as well, because since you are increasing the bandwidth, all the mobile terminals and the base stations, they are sharing the same bandwidth, which means it will bring some more interference as well. Because before, in the non-sharing mode, between each operator, the base stations are close. They have close access to the spectrum. But now they are open access. So what we have to do here is to analyze how this trade-off will be. Okay, here is a brief introduction to the stochastic geometry, which is the main tool I use to analyze this. Supposing that there is a mobile terminal which is located at the origin, the coverage probability that it receives it can be the probability that SINI is greater than a threshold, which SINI is defined as the signal to interference plus noise ratio. And the interference is you can see is the aggregate interference, which is on the third line. And here, if we can use the stochastic geometry, we can average everything. Average the distribution of the nodes, I mean the base stations or the base stations. We can average this distribution. We can average the channel fading between the base station and the mobile terminals. We can average the path loss between the base station and mobile terminals. We can also average the aggregate interference. So with the help of stochastic geometry, we can get a short expression like we see in the middle, which is the coverage probability can be written as an integration of a function. And it is good to notice that this MGF function it can be closed form. I mean, in this assumption, we are assuming that relay fading is used, so it can be closed formed. And it is quite easy to calculate this compared with if we are using the simulations to calculate this coverage probability. It can save a lot of time. And also it is mathematically tractable. The system model I'm using in this work is considering that a network consisting of two operators, two telecommunication operators, and the transmit power within each operator for every base station it is the same, and also the bandwidth for each operator it is the same. And we are assuming that the frequency and infrastructure resources are shared. And for the path loss model, it is not the simple path loss model, which is constantly for all the base stations or for all the distance. Using a one-ball path loss model, which means how do you say that? The path loss exponent for the LOS, long of sight links, and for non of sight links, they're different actually. And in this one-ball path loss model, we put this different. We considering this difference, and we're also considering the distance from the base station to the mobile terminals, which means if you have a different distance from the base station to the mobile terminals, it is different to if you have a different probability to have a line of sight path loss exponent or non-line of sight path loss exponent. Okay, and for the base station association, which means the mobile terminals will choose the base station as the intended base station based on the smallest path loss. And the data rate is defined as the theoretical achievable, which is the data rate, which is the channel capacity, as you can see here. To not get your too bored at the mathematical derivations, I will just present the results of my mathematical framework, which is for the non-sharing mode. The data rate can be seen as a summation of the two different data rates. And it is good to notice that the MGF function in the last line is also in closed form. And this is for the spectrum and infrastructure sharing mode, the final mathematical framework. The MGF function is also in closed form. To see that whether our mathematical framework it is valid, we also try to verify it in the simulations. You can see that the match is quite well. The x-axis it shows the radius of a base station, which means the higher of the radius, the lower density of the base station is. So you can see we will have a peak at some critical value of the radius, and we can achieve an optimal value of the data rate. And in this table, I presented we analyzed the optimal value of the data rate, which is the peak value you see here. Under in this table, the content in the table shows the optimal value of the data rate under the setting of the chosen setting of the parameters, which you can see the different ratio of the bandwidth, the different ratio of the transmit power. It is quite clear that if we are allowing the spectrum and the infrastructure sharing, we can achieve a much more better data rate, almost double in some cases. But I have to say that it is just for the current parameter setting, the system setting that I choose. For the other settings, it is we have to further analyze it. For the future work, we not only considering the data rate, we might analyze the area spectral efficiency for non-sharing and sharing cases, and then we might derive a more detailed mathematical framework. For example, with the consideration of the beamforming, shadowing, and other channel fading models, such like rising, Nakagami fading, like this. And then we hopefully, if we can help it with the network optimization, with the results we obtained. And also, currently we are considering the non-Poisson point process. For example, determinantal point process, hardcore point process, and